This is Shakil Ahmed. In this tutorial, we will discuss about using optimum function in R. Basically, we are interested in minimizing or maximizing some function. Then we use optimum command in R. So let's start with an example of ordinary square method where we minimize the residual sum of square to obtain the parameters alpha and beta. Uh, we have a model like y is equal to alpha plus beta x, then we are interested in estimating the parameter alpha and beta by minimizing the residual sum of square. So this is our data frame consisting y and x, and you can just run this function. I think this bracket is not closed, and you can just run the data, and we are interested in residual sum of squares. So we just create a function called minimum residual sum of square. I'm just making a function which input data and the parameters. So here we need to give initial values of the parameters and then optimize, and we will get the optimum values. So initially we can guess any value of the parameters. Parameter 1, that is intercept, and parameter 2, that is the slope coefficient, and x, then minus y minus y hat. Basically you can write y minus this thing, or vice versa. Basically this we are squaring, so it will not affect the result. So we can just run this function whether this function is working or not. This function is working perfectly. So then we need to give the initial values. We can just use the results, and we can just run this. And the initial value of the parameters are 0 and 1, and the data is the observed data. So we can basically, we are optimizing this function and with the parameters this, and the function is, you need to give three commands, basically the initial values and the function and the data, the three inputs. So the initial values, for example, I'm giving zero point 0.1 and then zero point 0.5, for example, and then function is minimize the residual sum of square, and then the data is the this data set. So you can just run this command. So this is the values we get, the parameters and the values, and then the function and the code, and then convergence. So you can see the parameters are minus 1.27 and 2.026 for the linear regression of y on x. So, and this is the value we get. The basically this is the minimum value of the residual sum of square, and this is the count of gradient, and how many times the function is iterated, and this is the convergence we achieved. If the convergence is not achieved, then the result, we can't rely on the result. So if we just run a linear model, so here ln y and x, and data is DAT. So you can just run this model, simple regression model, and again you can see the value is minus 1.26, that is rounded to minus 1.267, and the x value is 2.028, that is 2.029 rounded to this value. So we get the same values uh, for the regression coefficients, basically for the unknown parameters in this function. So this is the simplest way for getting the optimum values. And there are a lot of methods using Newton-Raphson and gradient descent, and different types of function you can use if you want to see more optimum function. You can just write optimum, and then you can search for the help for the and this function. You can just write optimum. You have the details about the optimum function here. So you have these different methods by default. This is giving, I think, the result is the Nelder-Mates method. Otherwise, there's CG and all these methods for. But these methods have different drawbacks and different good points as well. But it depends on the data. And the interesting thing, we can also find the estimates variance covariance matrix that is called the Hessian matrix. That is just inverse of the Hessian matrix. So we can get Hessian matrix of the estimates, and then that can be used as the, for example, if you want to see the standard errors, for example, Hessian results and Hessian. So you need to give the Hessian is equal to true in the option. For example, let's check it's the Hessian matrix is not shown for this case. You need to specify the Hessian matrix in your function basically. Hessian is equal to true, then it will get the Hessian matrix as well. You need to just specify here. Here. Hessian is equal to, so let's check. You will get the Hessian matrix as well. So interestingly, if you just find the inverse of the Hessian matrix, uh, that is basically the variance covariance for the two standard errors. This is this variance of sigma 1, and this is variance of sigma 2, and this is covariances of sorry, beta 1 and beta 2, and these are the covariances of beta 1 and beta 2. And if just this as